COVID situation ni, banyak sekali delivery datang. I think you also have faced the same problem, same issues lah. Okay, anak-anak saya dia suka beli online ni. Ya, ada je orang datang deliver. Okay, so back to this one, MSP offer often in practice. So maknanya sekarang ni becoming common. We not only produce one unit, but we produce many units. Okay, in injection molding, even in food making businesses, you make, for example, biscuit. Okay, you put in the acuan, not only one unit produced, but several units being produced. So we cannot use only a simple control one unit, what you call it, a simple as what we have seen as a univariate normal control chart. So we have to have innovation in monitoring such situation. Or we can have a separate control chart for each stream. So in this example, if we use individual control chart, meaning that you need 8 control charts, so it's going to be too much. Okay, maybe this is for number 1, another one going to be another control chart. So for example, this one you need going to have 8 control chart. So this is not attractive lah. Okay, having 8 control chart for this. So we need a better approach in this situation. Okay, we need a better approach. Okay, okay, so this is where this what we call it group control chart come in. Okay, group control chart. So in order to produce this, okay, okay, the average and range, okay, will be the average to produce a grand average and average R. So in this group control chart, okay, we call it group control chart for multiple stream. We have this. We still have the same formula here, okay, okay, and also for R chart, but the way that we calculate will be different, okay. Okay, for example, here they will be repeated until 20 subgroup. Okay, at this point they would have 20 multiplied by 6, so meaning that 120 averages of 4 observation each and 100 corresponding range. Okay, so the average range will be averages to produce a grand average X bar and average of R. Okay, so in this case, okay, if we follow this from beginning to illustrate this method, we construct and use the process that as, for example, 6 stream. Okay, let's say 6 stream. Stream here meaning that how many channel they produce. Okay, in the case of the bottle just now, the stream was 8. Okay, but in this example explanation here, let's assume that the stream is 6. And each stream has the same target and same inherent variability. Okay, assuming they are the same. So if they're not the same, it's going to be complex. So variable measurement is made on the item produced, and distribution of measurement is well approximated by normal. Okay, we assume that normally distributed. Okay, so sometimes people call it IID, identical and independently distributed, okay, to have it normal distribution. To establish a group control chart, the sampling is performed as if separate control chart were to be set up on each stream. Okay, so we assume like what we want to prepare individual chart. Suppose for the purpose of illustration, the sample size N is equal to 4. This means that 4 units will be taken from each of the S stream over a short period of time. Okay, so we know that when we do X bar chart, we take 4 unit or 5 unit, but in this case, we have 6. Okay. So in this case, we take 6 instead of taking 4. So what we have here is, for example, we take 20 subgroup, okay, 20 subgroup, and okay, you have here, let's say subgroup group 1, okay, until group 20, group 20 subgroup. At this point, we would have 20 multiplied by 6. Okay, let's say that you have 6 stream. Okay, this is product 1, product 2, product 3, product 4, product 6. Okay, so because the stream, every stream produce 6. Okay, so we would have 20 multiplied by 6. So total is 120 averages. Okay, 20 averages of n equal 4 observation each and 100 corresponding range. The average and range would be averages to produce the grand average. Okay, grand average. So the limit on the group chart would be, okay, this is the limit, and then we have same as also for R chart. So okay, how to understand this? 20 multiplied by 6 equal to 100. So this is every time the stream is coming as 6. Okay. Okay, I myself get confused now. Okay, what is this? So we have 120 averages of n equal to 4. Okay, let me check again the detail of this. Maybe, okay, let's go to ebook. Maybe ebook has something is missing from the slide. Okay, let me show you ebooks on this example. Okay, do you see the ebooks? Okay, please respond. You see the ebooks or not? All right, thank you, Muhammad Fitri. Okay, okay, this one is coming from this ebook on multiple stream, where we have multiple items at one time that we produce. Okay, okay, this is group control chart. Okay, control chart. Okay, we have 20 multiplied by 6 because 6 streams, so meaning that 120 averages. Okay, so where is the 4 unit coming? 4 unit coming. Okay, we don't have the example here, but anyway, it's okay. Let me check again on that explanation. For the time being, just hold on that one. Hold on to that one. Yeah, I will look into it. Yeah. how come we get 4 unit for every subgroup that we are having 6 stream? Okay, another challenge, okay, move on to another aspect of process monitoring is autocorrelated. Okay, autocorrelated. So autocorrelation in the process data, this is common, especially in automation. Okay, it's not identically and independently distributed. So we see here the data. Normally we make assumption. Okay, we make assumption that, okay, standard assumption. Okay, the control chart that we generate is they are normally and independently distributed. Okay, with mean and standard deviation. Okay, so when this is deviate, okay, from the assumption of normally and independently distributed, okay, especially for example in case of process is automated, okay, or the process is like a chemical processes, it does not follow this assumption. Okay. Okay, this assumption, okay, do not work well if the quality characteristic has even low level of correlation over time. Okay, when there is correlation, when is correlation happen? Correlation will happen, I say, in chemical processes, okay, or even in high-speed automation. So this will mislead, okay, will mislead the results. Okay, so it's mentioned here, include chemical processes. Okay, when we have chemical processes, okay, this issue we need to take care of it. Where conservative measurement on process or product characteristics are often highly correlated. Okay, highly correlated. Or in the case of automated tests and inspection procedure is being implemented, where we have automation, okay, there is tendency that they are correlated, meaning that the pieces that we produce, they are related. The piece that we produce now and the piece that we produce next one will have some correlation in terms of parameter that we monitor. Okay, if this is the case, okay, we need to have some modification in the control charting. Okay, so let's say this is a process variable with autocorrelation. This is we are plotting in terms of this is the time. Okay, this is the time, and this is what we measure. Okay, let's say that this is a time series data. We plot this. So, but when we plot, what we plot, xt, the current value. Let's say we have 1, we have 2, we have 3, and so on. So this point is considered as xt minus 1. This is xt. So let's say we are now here. So we are having xt. Okay, this one already become xt minus 1. Okay, xt minus 1. If we are comparing these two values. But when we move to the next point, okay, let's say we are now here. Point number 3. Okay, point number 3, and we look at x3 and x2. Is there any correlation or not? Okay, so this is what we are plotting here. You plot the previous value and the current value. Okay, for example, we plot number. Okay, let's say number in this case, number 63, okay, and 62. Is there any relationship or not? Okay, so for say number 65, okay, 65 here and 66. Okay, we look at that point. So if there is a shape like this, what we see here, the shape here, okay, in scatter plot, we know this is a scatter plot having positive, okay, positive relationship. There is correlation here. There is correlation in this case. So this is what we call the auto-correlated process, meaning that the previous values correlated with the next value. Okay, when we go to, for example, 70, okay, 70, and the current value is 71. Okay, we see, is there any correlation or not? Okay, it seems that there is correlation in this case because it's positively increasing. Okay, so this issue of correlated, where the data are auto-correlated, okay, the previous value correlated with the existing value. And we need to get this value of autocorrelation, okay, value of autocorrelation, normally represented by this symbol, okay, what is the value of correlation. So we can have positive correlation, negative correlation, and so on. I'm not going to go more detail on this, just to give you exposure that we have to be careful when there is autocorrelation happen. Autocorrelation happen in what situation? It happen when there is chemical processes and also when automation is being used. Okay? We have to be careful in using the control chart in such situation. So if we use Minitab, okay, Minitab is a statistical package where you can use this to solve many of control charting, the design experiment, and so on. So what you are doing manually now actually can be done using Minitab, but we have to learn how to do it manually, okay, before you can do it on computer. Otherwise, you may have mistake without understanding if you don't try manually. Okay, once you are familiar with the method, you can go ahead and put it in Minitabs. Okay, so the model that can be used in autocorrelation is, okay, we are looking into this time series model. Okay, time series model. Okay, so where we apply the control chart to the residuals. Okay, the residuals rather than the raw data. We look at the residual. Residual is actually how the data, like deviation, okay, deviate from the our target. Okay, so because we know that the residual, it will follow normality, it will follow the normally and independent distribution. So we can eliminate the aspect of autocorrelation by monitoring the residuals. Okay, so what we do is we remove the autocorrelation from the data. Okay, we remove the autocorrelation from the data and apply control chart to the residuals. Okay, so where this epsilon is normally and independently distributed, so we are monitoring this. Okay, where it has standard deviation of sigma and mean is 0. So if we see here, this is individual and moving range control chart. Okay, this example here, individual control chart, and this one is a moving range. We have learned this, moving range, individual chart. Okay, we also see that individual chart is very sensitive to the assumption of independent, of normality assumption. So, but when we put it, for example, this on the UMA chart, okay, we can see that how it shows. Okay, there are actually, it's not independent. They are basically, they are correlated. They are correlated, not as random as what we see from this individual chart. Okay, so different chart of the same data, it shows different. So there are I call it first order autoregressive. Sometimes people call it ARIMA, autoregressive model. Okay, so this is how you can get the residual. Okay, residuals ET equal to xt minus Okay, what is the predicted values? Okay, so or we call it the fitted, okay, the fitted value, okay, the fitted value from the model. So that give you the residual values. Okay, I think for the purpose of this course, I will not go in detail on this. There is require what you call deeper understanding on this modeling, time series modeling, and also we can use this EWMU as, also for the purpose of monitoring this based on EWMA, okay, EWMA to handle the autocorrelation. To handle autocorrelation. So we are monitoring the residuals rather than the raw data itself. Okay, you can see that it can become very complex when there is issues of autocorrelation. Okay, so the control chart can go more specialized. Okay, more specialized. It can go to, for example, monitoring toolware. Okay, monitoring specific cases. Okay, I also put in your slide this chart. Okay, this chart. So it can be used for you to look at how we can select control chart. Okay, some guidelines for univariate control chart selection. Here we have many charts. We have learned about, for example, X bar R, X bar S. We learned about Q sum. We learned about individual MR. Okay, so the decision which one to choose, okay, first can come from here. Are the data are auto-correlated? This is the first thing we have to ask. Okay, this is the data is correlated. If no, we can use this traditional method that we have learned here, this part. Okay, you have learned this part. Okay? There are many charts. Okay? And then when you look at it, okay, the data is variable or attribute. Okay, we have not learned about the attribute. Okay, hopefully by next class, I think I can start talking about this attribute. Okay, we have attribute control chart, we have variable control chart. So far we have discussed on variable. Okay, so and then we have to know whether n is greater than 1 or n equal to 1. Okay, is it n equal to 1 or is it greater than 1? So this is how we can select. Okay, if n equal greater than 1, we can use X bar R, X bar S. You can use also Q sum and EWMA. If the large shift, definitely has to go to XR or XS. If it is small, we can use Q sum and EWMA. But if n equal to 1, meaning the individual units is being monitored. If the shift is large, we can use X individual and MR. If the shift is small, you can use Q sum and EWMA. Okay, so the case that I was telling just now about autocorrelated, if it's autocorrelated, we go this way. Okay, if there is autocorrelated, so we go this way, autocorrelated. So is the model will be time series model, for example, ARIMA model. Okay, apply standard chart to either original data or residual data. Okay, residual data. So we compare the raw data, observed data, compared to the model, the predicted values. And then after that, we can use either X chart, MR, QSUM, or AAA. So the data is very important because we want to remove autocorrelation. Because to use this chart, okay, we have to satisfy the assumption of independent and identical normally distributed data. So if residual, of course, it's going to follow normal distribution. Okay. All right. So this chart guides us how to choose, because when you get a data or process, nobody will tell you what chart to use. Maybe in the textbook it tell you, okay, use this chart. But if you are given a data, you need to decide what chart it is most suitable to be used. Using wrong data, giving you the wrong assumption, wrong conclusion. Okay, there are more complicated aspects of this. For example, adaptive sampling procedure. Okay, so far we assume the procedure of sampling is the same. For example, you are taking at regular interval of n equal to 4, for example. But sometimes there are situations that require us to do adaptive. Adaptive meaning that it's not a fixed numbers that you have to follow. It's going to be changed depend on situation. Okay, so it's become more complex. Okay, we have an adaptive approach. Okay, of course, this application of control charting is dependent on the cost. So this involves economic design. It involves costing in collecting data, in making the testing of the sample. Sometimes sample has to be broken. You have to break the sample in order to know what is the quality characteristics. Okay, so cost become more important. So this is a more deeper aspect lah. I think we're not going to go in depth for this class lah. Okay, but you be aware that whenever we design control chart, we select the control limit, we select the frequency of data collection, we select the sample size. The impact is on the costing. Okay, the costing, because every sampling cost is related to the cost. Okay, so actually the textbook is very detailed and very go very deep on the monitoring. So I just want to show to you there is also control chart, what we call it toolware control chart. Okay, you have here, no, before that is control chart for healthcare monitoring. Okay, even in healthcare also can use for, okay, this is toolware control chart. This is very dedicated control charting for monitoring toolware. Like in machining, you have toolware in machining. Okay, so you can use this control chart for toolware, because when you use this tool, okay, and let's say this is your specification, your USL, lower specification limit, and this is the upper specification limit. Okay, specification limit, we know that designer determine the specification limit. Okay, so as long as it is within specification limit, the products still can be accepted by customer. But when we are plotting this, okay, we have control limit. Control limit is determined by process. Okay, you see that here within this specification limit. Okay, you can see that the distribution shifting. This is from here drifting up to here, but still within the control specification limit. Okay, it keep increasing. So in this case, okay, we cannot just simply decide that it is out of control, because the tooling is where worn out tooling. Okay, worn out the tooling. So there is a special chart for this. We call it toolware control chart. Okay, control chart for toolware. So because we are monitoring, it is within this limit. Okay, within this limit. So as long as it is drifting within this control limit, The control limit is somewhere here. Here, let me erase this. So you need to be clear on this. The difference between control limit and specification limit. So this is, oops. Okay, this is control limit. Okay, control limit is here. This is control limit. Okay, where it's distributed between plus minus 3 sigma. And this also the control limit. Okay, so in this case for toolware, the control limit here, this point, drifting, okay, upward. Okay, so it's drift upward. Okay, so but it's still within specification limit. Okay, within specification limit. So we give special treatment in this case. So we don't decide that it's out of control because it is related to the toolware. Okay, so you need to look at case by case, what suitable to be used. Okay, so there are many variations of that. Okay, I think I stop there for now. Okay, let me move back to, okay, so far we are discussing about univariate. Univariate. Okay, I want to touch on multivariate. Okay, multivariate control chart. Okay, this is a different aspect of process monitoring, okay, where we are having, okay, multivariate situation. Okay, I want to confirm with you. Do you see my slide multivariate now? All right, very good. Okay, multivariate. So we see that variation of control charting. And so far we have discussed multivariate, univariate. Okay, univariate. So, okay, for example, you are producing a bearing. So a bearing is not only one dimension that we, or one parameter that we monitor. We monitor more than one. For example, okay, to make it functional well, you may also interested to monitor. For example, in this case is you monitor internal diameter, and okay, internal diameter is important, and also the outer rings also important. Otherwise, this bearing will not work well. Okay, so a simple way to do this, okay, to do this is first you monitor. Let's say this is x1, and the other one is x2. Okay, the internal is x1, the other one is x2. So what we can do is to have two control chart. Okay, we have x1 here, the internal, this is the outer. But the problem now is going to be a valid control chart. Is it going to give you a good and reliable decision making? Okay, the answer is no. Okay, so we need to find a better method of monitoring. Okay, this is what we call it multivariate. Okay, multivariate process monitoring. Okay, before this, we just only univariate. Uni mean only one variable, only x1. Okay, so now we move to multivariate. But we only going to discuss about bivariate. Okay, the simplest form of multivariate is bivariate. Okay, bivariate where you have, okay, where you have two parameters to monitor. Okay, two parameters to monitor. More than two, we call it multivariate. Okay, so multivariate, it is more than two. Okay, so but the concept is the same. It's the same. It's referring to the same theory. Okay. Before I go there, just look at this outline. So actually, we still can use this very good, powerful EWMA for multivariate. Okay, multivariate. Some people using this multivariate. But if you want to use the traditional approach of Shewhart, they call it T2 control chart. Okay, T square control chart, or we call it hoteling. Hoteling is just a name of person. Okay, hoteling T2 control chart. Okay, for multivariate. Okay, or you can use have multivariate EWMA. Okay, multivariate EWMA. Of course, you can also have multivariate QSUM and so on. So, but I think if you know about multivariate EWMA, I think it's good enough, because QSUM is just alternative of another method of multivariates. Okay, so in practice, okay, many, if not most process monitoring and control scenario involve several related variables. For example, just now, internal diameter, outer diameter, they are related. You don't monitor only one parameter independently. Even for example, for assembly operation, okay? For example, you have a hole here and also another hole here. Okay, so these distances are related. Okay, if you get the correct dimensioning, if you get the correct dimension or distance, this point and this point. So how do we monitor this? Do you monitor? Do you monitor this based on, for example, to see this point? Okay, you monitor this point and this point, the distance from the corner, and this is from corner here to the other corner. Okay, or are you monitoring this also? Okay, are you also monitoring the center of this to the center of this? Okay, because if you want to put this hole to another place for assembly, okay, if one point here deviate without considering the other point, also you cannot go into the assembly line and assembly for the other parts. Okay, so meaning that this diameter also important. Okay, so perhaps also the other parameter, for example, distance of the corner to the center of this point, this corner to the center of this point, also important. So you may have over here maybe distance 2, distance 3. Okay, so it's not only one dimension or one parameter is enough. There are multiple parameters that need to be monitored. So just using simple independent single control chart is not enough. Okay, so this is what this statement here saying, that it involves several variables. Okay, although applying univariate control chart of each individual variable is a possible solution, but it is inefficient and also can lead to erroneous conclusion. Okay, so if we do it one control chart for D1, another control chart for D2, okay, another control chart for D3, okay, it is inefficient, okay, and also can give us error. We make wrong conclusion. So how to overcome this? To overcome this is by using multivariate method, okay, where we consider variable jointly consider. So we need to consider this jointly, meaning that simultaneously. Okay, I will stop there. So we take a break for 10 minutes and come back after that. Is it okay? All right, thank you. Muhammad Fitri, okay, thank you. Okay, we take 10-minute breaks. Okay, please, at least one person respond to me. Can we continue? All right, thank you, Najmi. All right. Okay, multivariate, what we discussed. So as I said just now that, okay, nowadays we not only monitor one parameter or one dimension, we have multiple dimension, okay, multiple parameters that require us to monitor. So this is because of the nature of the product. It's not only one parameter which is critical, but there are multiple characteristics. Okay, multiple characteristics. You have related parameters. Okay. Here we have this. Yes, we say that if you have multivariate, it will be inefficient and also may create errors if we use it individual control chart. Then we need to jointly monitor, have to be jointly monitored. Okay. Okay, let's say this example here. Okay, let's say example here of the bearing. Okay, so if we monitor individually, internal, external, yeah, we can monitor if it will be controlled, but at the end, in the application might not be useful because actually it's not in control, it's out of control. Okay, we need to see the correlation between X1 and X2. So how can we do that? Okay, can we do that? So this can be seen from here. Okay, if we do it individually, okay, let's say this is outer diameter. Let's say this is X1. X1 is, okay, monitor of one parameter here, X1, and we monitor the other one. Okay, this is, I put X double bar just to show the middle of this. So this is basically X1 and this is X2. So we're going to have two control chart. Okay, two control chart independently monitored. So the control region will be the control limits. So we have the control limits here. This is control limit for X1. This is a control limit for X2. So if we join this, it's going to be a box. Okay, a box. This is the line. This is a line. And this will be the another control lines for X2. So at the end, the control limit now become a square. Okay, not only just two lines, but it's going to be a box. Okay, if I extend that here in a bigger view, the box here actually is the control region. Okay, the box here. Okay, the control region is shown as a box. And the dotted point here is showing that, okay, the relationship between X1 and X2. So it shows that all the points within the box, so to make conclusion, it is in control. Okay, we make conclusion it's in control. But in practice, this is not correct. Okay, so this is not correct in practice. Why? Because actually, we are assuming they are independent, but actually it's not independent. They are dependent because we see that if internal diameter and external diameter, okay, they have to be jointly monitored because both are important. If you get internal diameter is in control, okay, it will affect also the outer diameter. It has to be jointly monitored. So how to do that? Okay, so we have to come up with another method of monitoring. I skip this one first. Let's see this here. So we put it. It is just the theoretical background of the multivariate, and this one is showing that the distribution of normal distribution when there is multivariate. it's not just a single. Normally we see just a single, but now it is two. We call this okay, we see in the three axes here. So it's going to be a shape like this. Okay, this is where the P or the parameter is 2. Okay, or what we call it bivariate. Okay, mathematically it shows density function. Okay, if we put in mathematics, so it looks scary, but don't worry so much about it. Okay, I want you to get the concept correct. The concept should be correct. So there is a background theory to it. Okay, so this you have x1 and x2, that two bivariate. Bivariate, they are correlated. So the shape is going to be like this. So it's not just a simple normal distribution. Now it's going to be showing this shape, which is explained by this relationship, this function. Okay, how can we simplify this? It looks complicated. Okay, so actually what we do is the box is not correct. Okay, so we have to have a joint control region which is showing in terms of ellipse. You see the shaded color here, the blue color. Actually, the blue color is the region of control, not the box, not the box. Okay, not the line. So the blue color is the joint region, where if it deviates outside the blue region, meaning that the process is out of control, because these are independent variables. Okay, the independent variable, okay, we have looks like a circle. Okay, not a box. Box is not correct for joint monitoring, but the circle is the correct one. The control region is given by the circle of the blue here. Okay, we see that all point within. Okay, no problem, because why? They are independent. They are not related, x1 and x2. Okay, the problem will happen when they are not independent. They are not independent. They are related. Okay, like this one. Okay. So when the ellipse, when they are dependent variables, like the one that we have in bearing just now, we have this diameter and another diameter. Okay, you need two diameter at least here to make it a bearing. Yeah, they are dependent each other. So now when they are dependent, you need an ellipse. Okay, this is ellipse, ellipse. The control region become ellipse. Not a circle, not a box. It is an ellipse. You see the blue here? The blue here is showing an ellipse. Okay, showing an ellipse, and there is one point outside the ellipse. You see this one point here? So actually that process that we see, we assume it was okay. Actually it was not okay. It's one point actually outside the ellipse. Okay, so the process is out of control. If we look individually, yes, it looks fine, looks okay, but when put it in ellipse, one point outside. So this is out of control. So from here, the meaning here is what we said earlier. Okay, it is misleading if we individually monitor. Okay, if we individually monitor x1, we individually monitor x2, it is misleading. We need to use, in this case, is two parameter. We call it bivariate. Okay, bivariate control chart. Okay, so the control limit is not a box of this line, not also a circle. It is an ellipse. Okay, why this ellipse? Okay, if you remember from scatter plot, okay, if you remember from scatter plot, we have many type of relationship. These are scatter plot. Okay, go back to basics of scatter plot. Okay, you can have, there is no correlation. Sorry, the image is not so clear. This is no correlation. No correlation is just distribute all over the place. Okay, no clear relationship between x1 and x2. But in the case of like this is a perfect positive correlation. You see here, perfect. Small value of x related to small value of x1 and x2. Small value of x1 related to small value of x2. Big value of x1 related to big value of x2. So meaning that these two values are correlated. If it is small, both are small. If it's big, both are big. But in this case, you see here, x1 is big, but x2 is small. Okay, you get this point. And this one, this value is small, but x2 is big. So there is no correlation. This correlation is 0. Okay, this one is correlation is 1. Positive, huh? This is positive 1. If you have 0.5 correlation, this is what you get. Okay, the ellipse will be like this, 0.5. This one, the ellipse will be thinner. Okay, and this is negative correlation. You have this negative 0.5. This is negative 0.9. Okay, this is perfect one lah, because one-to-one mapping. So this ellipse, okay, becoming important in joint monitoring. Okay, I want to get your feedback. You follow me or not so far? Please respond to chat box.
Doctor, I have a question. How do we decide that it is independent or dependent variable?
Okay, how do we decide that? Okay, very good question. So in the example of bearing, okay, definitely it is dependent because outer diameter and internal diameter, they are related. Okay, it's not independent. Okay, it's not independent because if you monitor internal, okay, let's say the internal is meeting the specification. Okay, but remember the specification there is minus and there are minimum value and low and maximum value. Okay, for example, I put it, let's say you have something here. Okay, let's say we give this diameter here of this, let's say 10 plus minus 1.0. Okay, and you get another one. Okay, the outer diameter, maybe this one is, let's say, 12 plus minus 1.0. Okay, so if you have here is 9 to 11. This is 9 to 11. Anything between you accept, right? This one is between 11 to 13. Okay, so you cannot have this one is let's say 9. Okay, this one is 13. It's going to be very loose. Your bearing is going to be very loose bearing. It is within spec if individually monitor. Let's say here is you have very small and this one is very large. Okay, so this is independent if you independently monitor. So what you need to do is, okay, you need to have a good fitting. Okay, a good fitting. You can have this is so small, this is so large. Okay, somehow there is overlapping there. Should be following like this, nah? Okay, if it is small, it should match with a small one. If it is big, it should match with a big one, so that you get the good fitting of your bearing. Okay, understand or not? Hello? Siapa tanya tadi? Is it make sense to you?
Yeah, Doctor. Okay.
Okay, so it means that it are not independent. This parameter is not independent. X1 and X2 for the case of application in bearing just now, it is not independent. It is dependent because if you have like this is individually monitoring this one, this is individually monitor. But at the end, when you try to assemble this, it's going to have a problem. Some are small, this one is big. So it's going to be a random like this. Will be random like this. So because it is independent. This is independent. So but for the purpose of functioning of this bearing, it should have good fitting. If you have a small, you should match with a small one. Same thing also when you are joining. For example, you are joining a let's say a bar. You have a bar. Okay, the male part, and you have a female part. Okay, let's say you want to put this into a hole. You want to put this in a hole. Okay, so you also have this plus minus something. This hole also plus minus something. If you take this is at the low side, go to here, is not going to properly fit. Okay, let's say again 10.0 plus minus 0.1. Okay, also maybe the whole here you also have the same thing. 10.0. Okay. Maybe for the whole you may have, okay, let's say you have the same, okay, 10.0, 0.1 also, right? Okay, so this is going to be 9.9 is the smallest one. The biggest one is 10.1. Why you need to have this tolerance? Because in any manufacturing, not possible to produce exactly 10. Yeah, I think that one is clear already, right? You're going to have some form of variability that you allow to vary plus minus 0.1. So you want to have a hole. In the hole also, the smallest hole will be 9.9 and the biggest hole will be 10.1. So if you want to put this into the application of this, okay, so you cannot have 9.9 to go into 10.1. Okay, there is a difference 0.2. So it's going to be just loose down and then not attached to it. Okay, faham kan? So somehow when you monitoring, for example, in this case, assuming they are producing using the related machine lah, okay, maybe not so in this case, but anyway, we see that the diameter of this, okay, are related to diameter of this. Okay, so somehow both have to be jointly monitored. Same thing also in the case of positioning. Let's say you want to feed in a pin. Okay, so this is another point, a pin. You got a piece of metal, okay, to come down here. Okay, how do you monitor this? Okay, how you monitor the process of punching this hole? Okay, let's say you want to assemble this. Okay, so not only the size of this important, not the size of this is important, not only the size, not only the size. We also, the importance is also the distance, okay, between this and this. Okay, the distance is also important. Okay, so meaning that the distance between this and this is also important. Okay, so it cannot be independently monitored. You cannot just have one control chart for diameter. Okay, let's say this is x1. and this is X2. Okay, so you cannot have independently. Okay, X1 one chart, X2 another control chart, cannot, because when you independently monitor, so you might have a quality problem when you are assemble these two pieces. Okay, so they are correlated, they are dependent, so it has to be jointly monitored when producing the hole. These two holes also have to monitor the distance. Okay, when meaning the control chart for distance and control chart for the diameter. I hope that clarify your the question. Is it okay? Okay, so how can we do this? How can we do this? Okay, as I say, now the control become ellipse. Why? Because they are dependent. Okay, they are dependent variables. Okay, so because looking at the ellipse not easy, not easy. So we can convert this into like a normal control chart here. This one is showing chi-square chart. Okay, chi-square chart, where the value here is in terms of chi-square. Okay, our upper control limit is determined by chi-square, and this chi-square actually is coming from. I think I have that formula somewhere. Okay, for the chi-square. Yeah, this is the formula for chi-square, where the X1 bar and X2 bar are sample averages of two quality characteristic computed from a sample of n. So we have two variables here. Okay, don't worry so much, it looks so complex here. Just to show you the background of it, but that control chart can be used with a simple more simplified version, what we call it T square. Okay, let me go back to the textbook on this. We have okay, please someone respond to me. You see the textbook or not? That is chapter 10 here. Okay, can someone respond? All right, you see, right? Okay, thank you. Al-Zamin. Okay, so we have here, okay, I move to this on chapter 11, chapter 11, continuation of my slide just now. Okay, so this is the chi-square chart. Okay, where the chi-square is able to capture, okay, the relationship between these two variables. Okay, and when chi-square is put into a matrix, it looks like this. It looks like this, where x bar is the mean, so the minus the mu, okay, and so on, and the control limit. And okay, so we can use this, what we call it, the T square control chart. Okay, totaling T square control chart, where the T is coming from. Okay, so what is important in this is what we have in the sigma here. Okay, okay, the sigma here, where we get the correlation, okay, matrix, correlation matrix. The correlation matrix. Yeah, I think if I show example, it will be easier. Okay, look at example 11.1. Okay, example 11.1. Okay, in this example, tensile strength and diameter. Okay, there are two parameters here, tensile strength and diameter of textile fiber of two important quality characteristics that are to be jointly controlled. Okay, tensile and diameter, jointly controlled. You have X1, which is tensile, X2 diameter. Okay, both have to be jointly monitored because they are correlated. The quality engineer has decided to use N equal to 10 fiber specimen each sample. He has taken 20 preliminary samples, and on the basis of this data, he concluded that, okay, so he calculate the mean, the center of X1, okay, this value, and the center for X2, this value, and he also calculate the standard deviation for S1, the standard deviation of S2, okay, and the covariance. This is the correlation. Okay, the correlation of S1, S12. S12 is the correlation of between 1 and 2, and set up a T2 control chart. So, okay, this is the data. Okay, this is the data given. Okay, so we have 20 data here. Okay, tensile strength and the diameter. Okay, the value given here is the mean. Already given the mean. So you got mean for tensile, sample number 1, the mean for diameter number 1, and so on. Okay, until you get the averages, the grand average for tensile, grand average for diameter. Similarly, we also calculate here the variance and covariance. So these are the variance. Okay, these are the variance. Remember, the variance is square root of standard deviation. Okay, this is variance. Variance is the square, not square root. The variance is the square of standard deviation. Okay, you have S2. S2 is the variance. If we put this in statistical package, it will easily give us these numbers. Okay, manually is quite tedious. So S12 is, we call it covariance. Okay, S12 is a covariance. Covariance. So we have these values here. Okay, so from the control chart that we want to establish is this one. Okay, this is the one which is we get a T square and this SK. Okay, the what we call standard deviation of that. Okay, so how we get the T square? Okay, this is the example of how we can calculate the T square. Okay, the T square. So it is coming from this here, the T square. So we have the N, we have the mean minus the grand mean, and we have this S, which is the standard deviation, minus 1, x minus x bar. So if we put it in this number into this formula, okay, so you have here 10, okay, remember you have that values, you have that here we have that here you have this part. Okay, hold on. T square. So because this is in terms of matrix, matrix representation. Okay, we have this covariance matrix. Okay, the covariance matrix S here. Okay, This is the covariance matrix. Okay, so where you have all these variants, all the variants, this variance here. Okay, so the covariance matrix S is the unbiased estimate of the sigma here. Okay, so you have that. So individual value of that is plugged in into this formula here to get all this, and then upper control limit. Okay, upper control limit is determined by this formula. Okay, the phase 2, when the chart is monitoring future production, the control limit is become as follow. Okay, the phase 2. The phase 1. Okay, this is the formula for the phase 1. Okay, remember the phase 1 is like a trial. Phase 2 is like the revised one where the process becomes stable. So okay, so the point here is when we have a process which are correlated, we can solve that problem using hoteling T2. Okay, hoteling T2 control chart. Okay, hoteling T2 control chart. In this example, where we have tensile, okay, related to diameter. Maybe you have a rope or something, maybe a wire. Okay, you want to push this wire. Okay, so the tensile of this also dependent on diameter. Okay, they are correlated each other. Okay, the bigger diameter, perhaps the tensile is getting better compared to a smaller diameter. Maybe tensile is smaller. So they want to see, okay, monitoring this, okay, the diameter and the tensile. So in this plot, if you see the plot here, it shows that everything is within control. Within control. Okay, so to decide the control limit, okay, this control limit is coming from this one. This control limit, you have P, in this case P is equal to 2 because we have only two parameters, x1 and x2. M minus 1, M is the number of subgroup which was 20. Okay, and N was I think 10, right? 10 minus 1. Okay, we have 10. So putting all this number and go to F. Okay, F table of this from this value. So you get this upper control limit. So lower control limit is not important. Not important. So okay, so another alternative of multivariate. Okay, another alternative of multivariate is we can use multivariate UMA. Okay, this one is multivariate UMA. We have seen before this univariate UMA, but now multivariate UMA. Okay, where exponentially weighted moving average can be used. Okay, can be used to monitor more than one parameter. Okay, so as we have seen earlier, the Z value here, so now become in terms of matrix. The dark color showing the matrix. Zi equal to lambda, same as before, this formula. So this table is just showing the performance of average run length of UMA at different value of lambda, okay, and the shift, how many shift. So at different parameter, you have two parameter, which is x1, x2. This one is x1, x2, x3, x4. Okay, the performance varies. So you can even use more than two parameters using this control chart. Okay, so the quantity plotted on the chart will be again t square. Okay, but the value here is z, z, which is the EUMA values. Okay, so yeah, I think that's all for exposure on the multivariate. So just be aware that when there is correlation, we cannot use individually. Okay, we can solve it using autolink T2, or we can solve it using multivariate EUMA or multivariate QSUM. Okay. So, okay, let me check. Is there anything else on this? Okay, you see that here they're using all these square and ellipse for monitoring. But this case is more elaborate on multivariate using principal component, partial. So I think it's beyond our scope. Okay. Okay, so if we look at this example, not example, the question here, 11.1, the data shows in table 11E1, which is this one, this one. So this data is coming from two parameters, x1 and x2. Okay, already given in terms of averages values. Okay, so you have 15 here. Yeah, I think only 15 sample, is it? So we should be 25, 15, 11.1. Okay, the data are sample mean of each quality characteristic based on the sample size of n equal 25. Okay, assume that the mean values of the quality characteristic and the covariance metric are computed from 50 preliminary sample. So what we can see here, okay, so it's given in terms of metric. So it means that the mean for x1 is 55. Okay, the mean for x double bar 2 is 30. Okay, this is given by this matrix. And this matrix is given the covariance. Okay, you have this covariance here. This covariance here, 200 and 120. This is the covariance of S12, sorry, S11 and N112. Okay, if you see from here, we have that covariance value. Okay, like what we have it, where we have it here. Okay, this value. Okay, so it's now this value are given. Okay, so we have variance and covariance, variance and covariance. This metric here, okay, covariance matrix. Okay, so in this matrix, so the matrix here is showing that, okay, you have S1, Okay, covariance. So in our case, it will be X. If we use X just now, right? So it's going to be X. Yeah, we're still using this S. Okay. Okay. We have covariance for the first one. Okay. So we have the variance for S1. It's covariance here. Okay, and then we have a variance for 2. Okay. So this one will be okay. So looking at this is what we have. So if we go back to the example of the question here, okay. So this is given here. This. So you have this equivariance, okay, 200, and this is 120, and then construct T2 control chart using this data, okay, using phase 2 control limits. Okay, so so I would like you to try to solve this 11.1, only one question here, okay, using this T2 square. Okay, and the formula to use is, okay, for the control limits, use the phase 2. That's what is mentioned. The phase 1 is like a trial. Phase 2 is when assuming the process is already stable, can be used for future monitoring. So the phase 2 formula is like, okay, this is the phase 1. Okay, yeah, this is the phase 2. Okay, this is the phase 2. Okay, this is the formula for phase 2. Okay, on page 522. All right, I think that's all for today. Any question before I finish? So what we have seen today is how we can address multivariate case where we are having at least 2 parameters that are correlated and they are related to each other. In example, in the case of internal diameter and outer diameter. So we have to jointly monitor this. We cannot have independently monitoring individual X1 independent and X2 because it's going to give a misleading conclusion. So the control limit will be in terms of ellipse, but this ellipse can be monitored in terms of T square, okay, T square. Alternative to T square chart is multivariate EWMA, but I want you just to be familiar with T square chart for monitoring 2 correlated parameters. Okay, any question before we end this session? Right, if there is no, thank you very much. Assalamualaikum warahmatullahi wabarakatuh.